Hi guys, today I'm going to be talking about conjugated polymers and their applications in electronics. And to understand this topic, we first need to look at what a polymer is and what a conjugated system is. So what is a polymer? A polymer is a molecule that is made up of multiple repeating subunits called monomers. They are represented by showing the repeating structure in brackets with the subscript N denoting how many monomer units are in the polymer. For example, polyethylene, shown in the bottom, is a polymer formed from multiple ethene molecules, shown in the top left, and it would be typically denoted as seen in the top right with the repeating structure shown with the subscript N. Conjugated systems are slightly more tricky to explain. They are a region of a molecule with connected p orbitals, which allows the electrons of said orbitals to move freely around the conjugated system of the molecule. These usually arise from alternating single and double bonds between carbons, as seen in the bottom left, and you need the right symmetry of the p orbitals for them to properly overlap with each other, causing this delocalized system as shown in the benzene ring. Now, in the top right, we can see an example of a molecule that isn't conjugated, even though it has alternating single and double bonds, because the shapes of the p orbitals don't allow overlap, and therefore is not conjugated. So if we put these together, we get conjugated polymers, which are polymers where the monomers are conjugated with the monomers to the left and right of it, creating a continuous conjugated system that spans across the entire polymer. These are particularly useful because the delocalized electrons are able to conduct electricity and therefore can be used in electronics. What are the advantages? Like most polymers, their properties can be finely tuned by introducing side chains or creating copolymers, which is a polymer made out of two different monomers. This means that they can be used in a wide range of applications because these different modifications give them different properties, which allows them to fit specific requirements. Also, as they are organic, it's easy to incorporate them into biological systems, making them extremely useful in bioelectronics. They are also cheaper and more easily processable than their organic counterparts. They have a wide range of applications. For example, bioelectronic devices, as we've said before, for example, artificial neurons, photovoltaic cells used in solar panels, light-emitting devices such as display screens, or plastic electronics like semiconductors. For the rest of the presentation, I'm going to be talking about polymer organic light-emitting diodes, or POLEDs, and how they utilize the electroluminescent properties of conjugated polymers. So how do they actually emit light? When you pass an electric current through a conjugated polymer, it promotes the electrons from the highest occupied molecular orbital, or HOMO energy band, to the LUMO energy band, or lowest unoccupied molecular orbital, in this case being the pi orbital and the pi star orbital, respectively. When these electrons then pass back down in energy, they release a photon of energy equal to the band gap that they passed. However, the main polymer I'm going to be looking at for the rest of the presentation is polyphenylene, or PPP, and its derivatives. Before we get into the real meat of the polymer, let's quickly look at how it's synthesized. Firstly, the benzene ring gains a proton. This is called the initiation step, and the benzene ring is turned into a cation. It can then react with a benzene ring, adding it to the ring, and once two hydrogens are removed, you'll be able to see that one of the benzene rings has been added to the reactive end. This continues happening over and over again until you have a certain number of benzene rings on the polymer, however many you want, and then it is terminated by finally removing the proton that activated the ring in the first place. One of PPP's major problems is that it is not solution processable, which is one of the main ways that the polymer is applied to a surface to create the final light-emitting product. We can overcome this limitation by adding solubilizing groups, such as alkyl groups seen below. However, the addition of alkyl groups to a single ring introduces torsion between the two rings, as seen by the angle theta. This reduces the conjugation of the polymer, resulting in the band gap increasing in energy, as seen before, causing the emission to shift from the visible region to the UV region, and obviously that means that the light that the diode emits is no longer visible. I've created two slides to better visualize this disruption in conjugation from steric effects. So, if we look down the two benzene rings, we'll see that in this example it's completely flat. The two benzene rings perfectly line up along each other, and so do the p orbitals. This means that the conjugation is perfect. If we now look onto the next slide, the benzene ring highlighted in orange has those alkyl groups and introduces the torsion in the bond. We can see that the ring behind it is now at an angle to the other ring, and this means that the p orbitals are slightly misaligned. This reduces the amount of overlap that the p orbitals can have and reduces the conjugation. In truth, unsubstituted PPP does actually have a torsion angle, albeit significantly less than substituted PPP. However, I decided to exclude this when I was first talking about it so that it was much easier to understand the concept. One of the solutions to this problem is bridging, where you connect two rings together, like shown above. This can reduce the torsion angle to or close to 0. And this allows us to put substituent groups on the other sides of the rings without creating the aforementioned steric effects. Let's quickly go into more view to understand how this works. So now that we're in more view, we can examine the 3D structures of the three bridges that we saw before. So firstly, the methine group. The carbon that connects these two rings is tetrahedron in shape. And the bonds that it connects the two rings with is perfectly straight along the bond, the other bond that connects the two rings normally. So if we look down the rings like that, we can see that they're completely straight and planarized. So that's why it's got zero degrees of torsion. If we just draw in the ethane bridge, we'll now see that because there are two carbons that are both tetrahedron in shape, the angles at which they connect the rings is slightly askew alongside this bond that is the other bond that connects the two rings, and that's what introduces that angle of torsion, that 20-degree angle of torsion along there that we saw on the slide. And when we add a double bond, making it an ethene bridge, because these carbons are now trigonal planar in shape, it's now completely flat again. Now that we're back, let's put all of this together. There are many bridges that I did not have time to discuss in this presentation, and they all have varying angles of torsion. This allows us to access the entire visible light spectrum through synthetic methods by fine-tuning which bridges we decide to use in which applications. Let's finish off where we started, with another synthesis, this time of methane-bridged BPP. As you can see, it is a copolymer reaction, as we need rings with substituent groups and other rings that will form the bridges between the rings. Now what's crucial is that this forms what's called an alternating polymer, where there is none of the same rings bonded to each other. This is achieved by putting bromine substituent groups on the bridging rings and boric acid groups on the substituted rings. These are only allowed to react with each other and not with themselves. And as you can see, this forms the alternating copolymer 2. We can then reduce the ketones on the bridging groups with lithium aluminium hydride, which then is able to form the bridges with other rings with a hydrolysis reaction, where the OH group on the bridging methine group is removed alongside the hydrogen of the opposing ring. That concludes the presentation, and these are just my references, which can also be found in the description below.